Deep learning has transformed the world of artificial intelligence, powering breakthroughs in computer vision, speech recognition, natural language understanding, and generative models. If you're preparing for interviews, this is your ultimate guide. Inside, you'll find 200 unique interview-style questions and answers, explained in a clear and practical way, just like you'd respond in a real interview. We'll start with the foundations of neural networks, move into training and optimization, explore regularization, CNNs, RNNs, advanced architectures, and finish with deployment, interpretability, ethics, and the future of deep learning. By the end, you'll not only know the answers, but you'll also know how to think and communicate like a deep learning engineer, confident, precise, and ready for real-world challenges. This is your complete deep learning interview prep blueprint. Let's dive in. What is a perceptron and how does it work? A perceptron is the simplest type of neural network unit inspired by biological neurons. It takes multiple inputs, applies weights, sums them, adds a bias, and passes the result through an activation function to produce an output. Essentially, it's a linear classifier that decides if input belongs to one class or another. While limited, it can't solve nonlinear problems like XOR perceptrons, laid the foundation for modern deep learning. Explain the architecture of a feed-forward neural network. A feed-forward neural network is the basic structure of deep learning models. Data flows in one direction from input layer to hidden layers to the output layer without loops. Each layer consists of neurons connected by weights, with biases adjusting thresholds. Activation functions introduce nonlinearity, allowing the network to model complex relationships. Training involves adjusting weights using backpropagation and gradient descent. What are activation functions and why are they important? Activation functions determine whether a neuron fires and introduce nonlinearity into the network. Without them, the entire network would act like a linear function, regardless of depth. Functions like sigmoid and tanh squash outputs into ranges, while ReLU accelerates training by avoiding saturation. Activation functions allow neural networks to learn complex, nonlinear patterns, critical for real-world tasks like vision or speech. Compare sigmoid, tanh, and ReLU activation functions. Sigmoid squashes values between 0 and 1, making it suitable for probabilities but prone to vanishing gradients. Tanh outputs between -1 and 1, centering data but still suffers from saturation. ReLU outputs 0 for negatives and raw input for positives, speeding training and mitigating gradient vanishing. However, ReLU can cause dying neurons. Each function has trade-offs, and the choice depends on the task and architecture. What problems does ReLU solve compared to sigmoid tanh? ReLU addresses the vanishing gradient issue common in sigmoid and tanh. By outputting linear values for positives, ReLU maintains stronger gradients, enabling deeper networks to train efficiently. It's also computationally simpler, improving training speed. However, ReLU introduces the risk of dead neurons if weights push outputs permanently negative. Despite this, it's the most widely used activation in modern deep nets. What is the vanishing gradient problem? The vanishing gradient problem arises when gradients shrink as they're backpropagated through deep layers, often with sigmoid or tanh activations. Small gradients mean weights barely update, stalling learning. This made training deep networks historically difficult. Solutions include using ReLU, like activations, better weight initialization, and architectures like LSTMs or RNNs that preserve gradients. What is the exploding gradient problem? Exploding gradients occur when gradients grow uncontrollably during backpropagation, causing unstable updates in divergent weights. This often happens in very deep networks or RNNs. Symptoms include NAN losses and oscillating parameters. Solutions include gradient clipping, careful initialization, and normalized architectures. Just like vanishing gradients, exploding gradients highlight the challenges of training deep nets. Explain backpropagation in neural networks. Backpropagation is the algorithm used to train neural networks by updating weights. It applies the chain rule of calculus to compute how errors in the output propagate back through each layer. Starting with the loss function, gradients are calculated for each parameter. These gradients guide adjustments via optimization methods like gradient descent. Backpropagation allows deep nets to systematically learn from data by reducing prediction errors layer by layer. What is the chain rule, and how does it apply to backprop? The chain rule states that the derivative of a composite function is the product of its inner derivatives. In backpropagation, outputs depend on weights through multiple layers, so we use the chain rule to compute how the error changes with respect to each parameter. Without the chain rule, it would be impossible to efficiently compute gradients in deep networks. Compare shallow versus deep networks. Shallow networks have only one or two hidden layers, while deep networks have many. Shallow models can solve simple tasks, but struggle with complex patterns. Deep networks learn hierarchical representations. Early layers capture low-level features, while deeper layers capture abstract patterns. While deep nets require more data and computation, they outperform shallow nets in tasks like image recognition or NLP. Why do deeper networks often generalize better? Deeper networks capture hierarchical structures in data. For example, in vision, early layers learn edges, mid-layers learn textures, and deeper layers learn objects. This multi-level abstraction enables better generalization to unseen data. However, generalization isn't guaranteed too much depth. Without regularization can lead to overfitting or vanishing gradients. What is the universal approximation theorem? The universal approximation theorem states that a feed-forward neural network with a single hidden layer and sufficient neurons can approximate any continuous function. While powerful in theory and practice, deeper architectures are more efficient and scalable. The theorem highlights neural networks' flexibility, but doesn't solve challenges like training, optimization, or generalization. What is the role of weights and biases? Weights determine the strength of input signals in a neural network, while biases shift activation thresholds. Together, they shape how neurons transform inputs into outputs. Weights capture feature importance, and biases add flexibility, ensuring the network isn't restricted to passing through the origin. Proper initialization and training of weights and biases are essential for learning. What is weight initialization? Weight initialization sets starting values for network parameters before training. Poor initialization can lead to vanishing or exploding gradients, slowing or preventing convergence. Good strategies like Xavier or He initialization scale weights relative to layer size, stabilizing training. Initialization is a subtle but critical factor in training efficiency. Compare Xavier versus He initialization. Xavier initialization sets weights based on the number of input and output neurons, ideal for sigmoid or Tanch activations. He initialization scales weights larger, tailored for ReLU activations to maintain variance. Using the wrong scheme can destabilize gradients. Choosing Xavier versus He depends on the activation function, showing how tightly coupled initialization is to architecture design. What is a cost and loss function in neural networks? A cost function measures how well predictions match actual outputs. It quantifies model error to guide optimization. For regression, MSE is common. For classification, cross-entropy loss dominates. The choice of cost function must align with the problem. It's the compass that directs weight updates during training. Compare regression versus classification loss functions. Regression typically uses MSE or MAE, focusing on minimizing continuous prediction errors. Classification uses cross-entropy loss, which penalizes incorrect probabilities more heavily, encouraging accurate confidence estimates. While regression losses measure distance, classification losses measure probability misalignment. Choosing the right loss ensures the model optimizes for the correct objective. What are hyperparameters in neural networks? Hyperparameters are external settings not learned during training, but defined beforehand. Examples include learning rate, batch size, number of layers, neurons per layer, dropout rate, and weight initialization. They control the learning process and heavily influence performance. Tuning hyperparameters is often as important as model design. How do you choose activation functions? Activation choice depends on the task and architecture. Sigmoid works for binary outputs, softmax for multi-class probabilities, and ReLU for hidden layers due to efficiency. Variants like leaky ReLU or GELU address ReLU's dying neuron issue. The decision balances interpretability, gradient flow, and computational efficiency. Often ReLU dominates hidden layers, while output layers use task-specific activations. What is softmax and why is it used? Softmax converts raw scores into probabilities that sum to 1, making it ideal for multi-class classification. Each class receives a probability proportional to its score, allowing comparison across categories. It enables models to output interpretable predictions like 70% cat, 20% dog, 10% horse. Softmax turns logits into actionable probabilities. What is gradient vanishing in RNNs versus feed-forward nets? While vanishing gradients affect all deep nets, it's worse in RNNs due to repeated multiplication through long-time steps. This prevents RNNs from learning long-term dependencies. Feed-forward nets can suffer too, but skip connections and ReLU mitigate the problem. LSTMs and GRUs were specifically designed to address vanishing gradients in sequential data. How do skip connections, ResNets, solve vanishing gradients? Skip connections let gradients bypass certain layers by adding the input of a layer directly to its output. This creates shortcut paths for gradient flow, preventing them from vanishing in very deep networks. ResNets popularized this idea, enabling networks hundreds of layers deep to train successfully. Skip connections are a cornerstone of modern DL architecture design. What is a biased neuron and why is it needed? A biased neuron is an extra parameter that shifts the activation function left or right. Without it, all activations would pass through the origin, limiting flexibility. Bias terms allow models to represent a broader range of functions by adjusting thresholds. In short, they let neurons fire even when inputs are zero. What is the difference between capacity and complexity? Capacity is a model's ability to fit a wide variety of functions, while complexity is the actual number of parameters or layers. High-capacity models can approximate complex patterns, but excessive complexity risks overfitting. Striking the balance, enough capacity to capture structure, but not so much that it memorizes noise, is critical for good generalization. What is the role of nonlinearity in neural networks? Nonlinearity, introduced by activation functions, allows networks to learn complex mappings. Without it, multiple layers would collapse into a single linear transformation, no better than linear regression. Nonlinearity enables deep nets to model intricate real-world data from speech to vision. It's the essential ingredient that makes neural networks powerful. What is stochastic gradient descent (SGD)? Stochastic gradient descent updates model weights using a single sample, or small batch, at a time instead of the full dataset. This makes training faster and introduces noise, which can help escape local minima. While less stable than full batch methods, SGD is the backbone of deep learning optimization. Its efficiency and scalability make it the default choice for large datasets. Compare batch, mini-batch, and stochastic gradient descent. Batch gradient descent computes gradients on the entire dataset, stable but slow. Stochastic gradient descent updates for every single sample, faster but noisy. Mini-batch gradient descent strikes a balance. Using small batches, like 32 or 128 samples, it combines efficiency with stable convergence. Mini-batch is most common in practice, especially with GPU acceleration. What is momentum in optimization? Momentum accelerates SGD by adding a fraction of the previous update to the current step. It smooths oscillations in directions with noisy gradients and speeds convergence in valleys of the loss landscape. Think of it as pushing a ball downhill. It keeps rolling, reducing zigzagging. Momentum helps models converge faster and more reliably. Explain Nesterov accelerated gradient. Nesterov accelerated gradient, ENAG, is an improvement over momentum. Instead of calculating gradients at the current position, it looks ahead to where momentum would take the parameters. This anticipatory step provides a corrective adjustment, often converging faster and with more precision. NAG combines speed with stability, making it popular in advanced optimizers. What is Autograd and when to use it? Autograd adapts learning rates per parameter based on historical gradients. Frequently updated features get smaller steps, while rare ones get larger updates. It's great for sparse data like text or clicks. However, learning rates continuously shrink, sometimes halting progress. While outdated for deep nets, Adagrad laid the foundation for adaptive optimizers like RMS-prop and ADAM. What is RMS-prop and why was it introduced? RMS-prop fixes Adagrad's shrinking learning rate problem by using a moving average of squared gradients. This prevents step sizes from decaying to zero. It balances updates, making it effective for non-stationary problems like reinforcement learning. ARMS-prop is lightweight, fast, and remains widely used for sequence-based tasks. Explain ADAM optimizer. ADAM combines momentum, first moment estimates, with RMS-prop, second moment estimates. It adapts learning rates for each parameter while keeping updates smooth. ADAM requires little tuning, converges quickly, and works well across diverse problems. It's often the default choice in deep learning. However, ADAM can sometimes overfit or plateau compared to SGD with momentum, so the choice depends on the task. Compare ADAM versus SGD. SGD with momentum is simple, robust, and often leads to better generalization, but it requires careful tuning. ADAM adapts learning rates automatically, making it faster and easier for noisy or sparse problems. In large-scale training, ADAM is preferred for speed, while SGD often wins in fine-tuned performance. Many practitioners start with ADAM, then switch to SGD for the final training stages. What is ADAM-W and why is it better than ADAM? ADAM-W decouples weight decay from gradient updates, fixing a flaw in ADAM's regularization. In ADAM, L2 regularization is scaled incorrectly, leading to suboptimal generalization. ADAM-W applies weight decay directly, making optimization more stable and improving performance. It's now the recommended variant in many frameworks. What is a learning rate schedule? A learning rate schedule adjusts the learning rate during training. High rates help escape poor minima early, while lower rates refine convergence later. Schedules can decay exponentially, stepwise, or adapt dynamically. Proper scheduling accelerates training and improves final accuracy. What are cyclical learning rates? Cyclical learning rates oscillate between a lower and upper bound during training. Instead of monotonically decreasing, they allow the model to explore wider regions of the lost landscape before settling. This helps escape saddle points and can lead to faster convergence. It's a practical trick for improving accuracy without extra computation. What is gradient clipping? Gradient clipping limits the magnitude of gradients during backpropagation. It prevents exploding gradients, especially in RNNs or very deep networks. By capping gradients at a threshold, training remains stable. It's a simple yet essential safeguard in many DL pipelines. What is exploding gradient and how do you handle it? Exploding gradients happen when values grow uncontrollably, causing NANs or divergence. Common in deep nets or RNNs, symptoms include unstable losses. Solutions include gradient clipping, careful weight initialization, normalized layers, and using optimizers like RMS-prop. Managing exploding gradients is crucial for stable training. What is gradient checking? Gradient checking validates backpropagation by comparing analytical gradients with numerical approximations. A small perturbation is applied, and the loss change is observed to compute numerical gradients. If they match, backprop is likely correct. It's a debugging tool used in early stages of model development to ensure correctness. What is convergence in training? Convergence means the model's loss stabilizes and further training doesn't improve significantly. It indicates the optimization has reached a local or global minimum. Monitoring validation metrics ensures convergence isn't just overfitting. Proper convergence reflects a balance between learning rate, optimization, and model capacity. What is local minima versus saddle point in DL optimization? Local minima are points where loss is lower than nearby areas, but not globally lowest. Saddle points, more common in high dimensions, are flat regions where gradients vanish, but loss isn't minimal. Singapore dollar noise helps escape both by injecting randomness into updates. Deep nets usually don't get stuck in true local minima, but saddle points can slow training. What is batch size, and how does it affect training? Batch size determines how many samples are processed before weights update. Small batches improve generalization but are noisier. Large batches converge faster, but risk sharp minima and poor generalization. GPU memory often dictates practical batch size. Striking a balance as key values like 32 or 64 are common defaults. What is an epoch versus an iteration? An epoch is one full pass through the training dataset. An iteration is one parameter update, typically after a mini batch. If you have 10,000 samples with batch size 100, that's 100 iterations per epoch. Understanding this distinction helps when setting schedules and monitoring training progress. What is warm-up in training schedules? Warm-up gradually increases the learning rate at the start of training instead of starting high. This prevents instability when weights are randomly initialized. After the warm-up phase, learning rate follows the normal schedule. It's particularly important in large-scale training, like transformers, where high learning rates early can derail optimization. How do you detect convergence during training? Convergence is detected by monitoring loss and validation metrics. If both flatten or stop improving for several epochs, training may have converged. Early stopping can automate this process. Care must be taken. Sometimes a plateau is temporary, and further training with learning rate decay can yield improvements. What is early stopping? Early stopping halts training when validation performance stops improving, even if training loss decreases. It prevents overfitting by stopping before the model memorizes noise. Early stopping is a practical form of regularization, saving time and resources while improving generalization. How do GPUs and TPUs accelerate optimization? GPUs parallelize matrix operations, which dominate neural network training, making them far faster than CPUs. TPUs go further, being specialized for tensor operations with optimized hardware. These accelerators reduce training time from weeks to hours, enabling deep learning's modern breakthroughs. Without them, today's large-scale models would be impractical. What is mixed precision training? Mixed precision training uses both 16-bit and 32-bit floating-point arithmetic to speed up training while reducing memory usage. Modern GPUs support this natively. It accelerates training without sacrificing accuracy, as critical calculations remain in higher precision. It's now standard practice for training large-scale deep learning models efficiently. What are learning rate warm restarts? Learning rate warm restarts periodically reset the learning rate to a higher value during training, then decay it again. This helps the optimizer escape shallow minima and explore better solutions. It's similar to cyclical learning rates, but with scheduled resets. Warm restarts often improve convergence in complex loss landscapes. What is loss landscape in DL? The loss landscape represents how the loss function varies with model parameters. In deep nets, it's highly non-convex with valleys, plateaus, and saddle points. Understanding the landscape helps explain challenges like vanishing gradients, sharp versus flat minima, and generalization. Visualizing loss surfaces shows why certain optimizers or batch sizes improve training dynamics. What is overfitting and how to prevent it? Overfitting happens when a model learns training data too well, including noise, and fails to generalize to unseen data. It shows up as low training error, but high validation error. To prevent it, we use techniques like dropout, L2 regularization, data augmentation, and early stopping. Gathering more diverse data also helps reduce overfitting. What is underfitting? Underfitting occurs when a model is too simple to capture underlying patterns in the data. It shows high error on both training and validation sets. Causes include insufficient model complexity, poor features, or inadequate training. Fixes include adding layers, tuning hyperparameters, or providing richer data representations. Compare bias versus variance. Bias is error from overly simplistic assumptions, leading to underfitting. Variance is error from excessive sensitivity to training data, leading to overfitting. The trade-off is balancing both. Too much bias ignores patterns, too much variance memorizes noise. Regularization, ensemble methods, and more data help manage this trade-off. What is dropout and why is it effective? Dropout randomly disables a fraction of neurons during training, forcing the network to rely on multiple pathways. This reduces co-adaptations and prevents overfitting. At inference, all neurons are active, but outputs are scaled. Dropout acts like ensembling within a single network, improving robustness and generalization. What is batch normalization? Batch normalization normalizes activations within a mini-batch. ensuring consistent distributions across layers. It stabilizes training, allows higher learning rates, and reduces dependence on careful initialization. By adding scale and shift parameters, it preserves model flexibility. Batch norm is standard in deep architectures to improve both speed and accuracy. Compare layer norm versus batch norm. Batch norm normalizes across the batch dimension, making it sensitive to batch size. Layer norm normalizes across features within a single instance, making it more stable for small batches or sequence models like transformers. While batch norm suits CNNs, layer norm is widely used in NLP models. What is weight decay? Weight decay is a form of L2 regularization that penalizes large weights by shrinking them during training. This encourages simpler models and reduces overfitting. In optimizers like AtomW, weight decay is applied directly to parameters, improving generalization. It's a lightweight yet powerful regularization tool. What is label smoothing? Label smoothing replaces hard one-hot targets with slightly softer probabilities. Instead of 0, one labels might be 0.1, 0.9. This prevents the model from becoming overconfident, improving calibration and generalization. It's common in classification tasks like image recognition and NLP. What is data augmentation in DL? Data augmentation artificially increases training data by applying transformations like rotations, flips, or noise. It prevents overfitting by making the model invariant to minor changes. In vision, it includes crops, color jitter, or cut mix. In NLP, techniques like synonym replacement are used. Augmentation improves robustness without collecting new data. What is early stopping as regularization? Early stopping halts training when validation performance plateaus, even if training error keeps dropping. This prevents the model from memorizing noise. It's simple, requires no extra computation, and is one of the most effective regularization methods in practice. What is mix-up training? Mix-up creates new training samples by blending two inputs and their labels, like combining images and interpolating labels. This encourages the model to behave linearly between classes, improving robustness. It reduces overfitting and improves performance on out-of-distribution data. Mix-up is particularly effective in image classification. What is cut mix? Cut mix replaces a random patch of one image with a patch from another, adjusting labels proportionally. Unlike mix-up, which blends entire images, cut mix maintains sharp object boundaries. It acts as both augmentation and regularization, improving performance in CNNs. It encourages models to focus on all regions, not just discriminative parts. How do ensembles reduce overfitting? Ensembles combine predictions from multiple models, reducing variance by averaging out noise. While a single model may overfit, ensembles of diverse models generalize better. Bagging, boosting, or stacking are common ensemble methods. Though computationally expensive, ensembles often deliver state-of-the-art performance. What is the generalization gap? The generalization gap is the difference between training performance and test performance. A small gap means the model generalizes well, while a large gap indicates overfitting. Monitoring this gap helps decide when to regularize, stop training, or collect more data. How do you detect model overfitting during training? Overfitting is detected when validation loss starts increasing while training loss continues to decrease. Metrics like accuracy or F1 also diverge between training and validation sets. Visualization of learning curves is the simplest way to detect overfitting. What is knowledge distillation? Knowledge distillation transfers knowledge from a large teacher model to a smaller student model. The student is trained on soft probabilities output by the teacher, not just hard labels. This enables smaller models to achieve competitive accuracy with lower computational cost, ideal for deployment on edge devices. How does pruning help generalization? Pruning removes less important weights or neurons, reducing model size and complexity. It prevents overfitting by simplifying the network, similar to regularization. Beyond generalization, pruning also speeds inference and reduces memory usage, making models more efficient without much accuracy loss. What is quantization? Quantization reduces the precision of weights and activations, for example, from 32-bit floats to 8-bit integers. It shrinks model size, speeds up inference, and reduces memory usage. While primarily for efficiency, Quantization can also act as a mild regularizer by smoothing weights. It's widely used in mobile AI deployment. How do dropout rates affect training? Low dropout rates, like zero point 0.1, may have little effect, while very high rates, 0.7 plus, hinder learning. Typical values are 0.2 to zero point 0.5. Too much dropout underfits, too little risks overfitting. The ideal rate balances robustness and training efficiency, often tuned experimentally. What is spectral normalization? Spectral normalization constrains the Lipschitz constant of a layer by normalizing weight matrices using their largest singular value. This stabilizes training, particularly in GANs, preventing exploding gradients and mode collapse. It improves generalization by controlling layer sensitivity. How do you validate generalization on small datasets? On small datasets, k-fold cross-validation is critical to get stable estimates. Data augmentation and transfer learning from pre-trained models also help. Regularization techniques like dropout and early stopping are especially important. Ultimately, collecting more data is the best solution. What is adversarial training? Adversarial training improves robustness by adding adversarially perturbed examples to the training set. These are inputs intentionally modified to fool the model. By learning from them, the model becomes more resistant to attacks and overfitting. It's a form of data augmentation for security. What is contrastive learning as regularization? Contrastive learning trains models to pull similar pairs closer in latent space and push dissimilar pairs apart. It improves representation learning without labels. As regularization, it forces the model to learn robust features that generalize better. SimCLR and BYOL are popular contrastive learning approaches. What is the double descent phenomenon? Double descent describes how test error first decreases, then increases, and finally decreases again as model capacity grows. Classical ML predicts U-shaped error, but deep nets show this double descent. It means over-parameterized models can generalize surprisingly well, challenging traditional bias variance trade-off assumptions. Why does larger data improve generalization? Larger datasets expose models to more diverse examples, reducing the chance of memorizing noise. This lowers variance and improves generalization. With enough data, even very large models can perform well without overfitting. Data scale is often more important than algorithmic tweaks. What is convolution in CNNs? Convolution is the process of sliding a filter kernel over input data to extract local features. Each filter detects patterns like edges, textures, or shapes. Instead of fully connecting every neuron, convolution preserves spatial structure while reducing parameters. This local connectivity makes CNNs efficient and well-suited for images, where nearby pixels are strongly correlated. What is stride in convolution? Stride defines how far the filter moves after each operation. A stride of 1 means moving pixel by pixel, while higher strides reduce output size by skipping locations. Larger strides shrink feature maps, speeding computation but risking information loss. Stride controls resolution versus efficiency in CNNs. What is padding in CNNs? Padding adds extra pixels, usually zeros, around the input before convolution. It preserves spatial dimensions, allowing filters to cover edge regions. Without padding, feature maps shrink after each layer, limiting depth. Same padding keeps size constant, while valid padding uses no extra pixels. Padding helps CNNs learn better from border information. Compare max pooling versus average pooling. Max pooling selects the maximum value in each region, capturing strong features and reducing noise. Average pooling takes the mean, preserving overall information, but smoothing details. Max pooling is more common in practice because it emphasizes dominant patterns, like sharp edges, which are crucial in vision tasks. What is global average pooling? Global average pooling replaces fully connected layers by averaging each feature map into a single value. It drastically reduces parameters and prevents overfitting. For example, in classification, each average value corresponds to a class score. It's widely used in modern architectures like ResNet for efficiency and interpretability. Why do CNNs work well for images? CNNs exploit spatial locality. Pixels near each other are more related than distant ones. Convolutions capture local patterns, and stacking layers builds hierarchical features. Edges, arrow textures, arrow objects. Weight sharing reduces parameters, making CNNs scalable. This combination of efficiency and hierarchical representation makes CNNs the standard for image tasks. What is receptive field in CNNs? The receptive field is the region of the input image that influences a neuron's output. Small in early layers, it grows deeper in the network, covering larger areas. This allows deeper layers to detect complex patterns like objects, while early layers capture edges or textures. What is a kernel or filter in CNNs? A kernel or filter is a small matrix of weights applied to the input to detect features. Different filters capture different patterns, like vertical edges, corners, or textures. Multiple filters per layer allow CNNs to learn diverse representations automatically from data. What is parameter sharing in CNNs? Parameter sharing means the same filter weights are applied across all spatial positions. This drastically reduces parameters compared to fully connected layers and ensures translation invariance. A filter that detects an edge in one part of an image will detect it anywhere, making CNNs robust to position shifts. Explain Linnet architecture. Linnet, introduced in the 1990s for digit recognition, was one of the first CNNs. It consists of two convolution plus pooling layers, followed by fully connected layers. Linnet used tan-H activations in small kernels. Despite its simplicity, it pioneered concepts like convolution, pooling, and hierarchical feature extraction, influencing all modern CNNs. Explain AlexNet architecture. AlexNet won the 2012 ImageNet competition, sparking the deep learning boom. It had 5 convolutional layers, ReLU activations, max pooling, and 3 fully connected layers. AlexNet introduced dropout to reduce overfitting and leverage GPUs for large-scale training. Its dramatic accuracy leap over traditional methods proves CNN's power on big data. Explain VGG-Net architecture. VGG-Net, introduced in 2014, used very deep networks, up to 19 layers, with a simple design, stacked 3 by 3 convolutions and max pooling. It showed that depth improves performance. VGG-Net achieved high accuracy but was computationally expensive due to its massive parameter count. Its simplicity made it a popular baseline. Explain ResNet and skip connections. ResNet solved the problem of vanishing gradients in very deep networks by introducing skip connections or residual blocks. These allow inputs to bypass layers, letting gradients flow directly backward. This enabled networks with hundreds of layers to train successfully. ResNet remains a cornerstone of modern vision architectures. What is DenseNet? DenseNet connects each layer to all subsequent layers, so every layer receives feature maps from all previous ones. This improves feature reuse, strengthens gradient flow, and reduces parameters. DenseNet achieves high accuracy with fewer weights than ResNet, but can be more memory-intensive. What is EfficientNet? EfficientNet scales networks systematically by balancing depth, width, and resolution with a compound scaling method. Instead of arbitrarily making models bigger, it optimizes scaling to maximize accuracy while minimizing computation. EfficientNet models are state-of-the-art for accuracy or efficiency trade-offs, widely used in real-world applications. What are depth-wise separable convolutions? Depth-wise separable convolutions split convolution into 2 steps. Depth-wise, per channel filtering, and point-wise, one-by-one convolution to combine channels. This drastically reduces computation and parameters. It's the key innovation behind MobileNet, making CNNs efficient for mobile and edge devices. What are dilated convolutions? Dilated, or Strauss, convolutions insert gaps between filter weights, enlarging the receptive field without increasing parameters. They capture multi-scale context, making them popular in semantic segmentation tasks. Dilated convolutions balance detail with broader context in image analysis. What is group convolution? ResNext. Group convolution divides input channels into groups and applies convolution separately, then merges outputs. This reduces parameters while maintaining accuracy. ResNext popularized this, showing that increasing cardinality groups improves performance more efficiently than just adding depth or width. What is inception architecture? Inception networks use parallel convolutions of different sizes, 1 by 1, 3 by 3, 5 by 5 within the same layer, capturing multi-scale features. They also use 1 by 1 convolutions to reduce dimensionality before expensive operations. This design, introduced in GoogleNet, achieves state-of-the-art accuracy with fewer computations, influencing later architectures. Compare CNNs versus vision transformers. CNNs excel at local feature extraction with strong inductive biases for vision tasks. Vision transformers, VITs, use self-attention to capture global relationships without convolutions. VITs outperform CNNs with enough data but require larger datasets in compute. CNNs remain efficient and robust for smaller datasets, while VITs dominate at scale. What is transfer learning in CNNs? Transfer learning reuses pre-trained CNNs trained on large datasets like ImageNet. Lower layers act as feature extractors, while upper layers are fine-tuned for a new task. This saves computation, improves performance on small datasets, and is standard practice in computer vision. How do you fine-tune pre-trained CNNs? Fine-tuning involves initializing a model with pre-trained weights, freezing some layers, often early ones, and retraining later layers on new data. This adapts general features like edges into domain-specific patterns. Learning rates are typically lower to avoid disrupting pre-trained weights. What is feature extraction versus fine-tuning? Feature extraction uses a pre-trained CNN as a fixed feature generator, training only a new classifier on top. Fine-tuning updates some or all pre-trained layers with new data. Feature extraction is faster and safer for small datasets, while fine-tuning achieves higher accuracy with sufficient data. What is freezing layers in CNNs? Freezing layers means preventing weight updates during training. Typically, early CNN layers are frozen since they learn general patterns like edges. Later layers, more task-specific, are retrained. This saves computation and avoids overfitting, especially when labeled data is limited. How do you use CNNs for object detection? CNNs form the backbone of object detection models. Architectures like faster RCNN generate region proposals and classify them, while YOLO and SSD predict bounding boxes and classes directly in one pass. CNNs extract hierarchical features, which detection heads use to locate and classify objects. Object detection combines CNN feature extraction with region or grid-based prediction methods. What is an RNN, and how does it differ from a feed-forward NN? A recurrent neural network, RNN, is designed for sequential data. Unlike feed-forward networks, which process inputs independently, RNNs maintain a hidden state that carries information from previous steps. This recurrence allows them to model temporal dependencies, making them suitable for text, speech, or time series tasks. However, standard RNNs struggle with long sequences due to vanishing gradients. What is the vanishing gradient problem in RNNs? In RNNs, backpropagation through time multiplies gradients repeatedly across many time steps. With activations like tan-H or sigmoid, gradients shrink toward zero. This vanishing effect makes it nearly impossible to learn long-term dependencies. As earlier signals fade before reaching the output, it's one of the key limitations of vanilla RNNs. How do LSTMs solve vanishing gradients? Long short-term memory, LSTM networks solve vanishing gradients with a memory cell and gating mechanism. The input, forget, and output gates control how much information flows in and out, allowing important signals to persist over long sequences. By preserving gradients through the cell state, LSTMs effectively capture long-term dependencies in sequential tasks. What is a GRU, and how is it different from LSTM? Gated recurrent units, GRUs, simplify LSTMs by combining input and forget gates into an update gate. GRUs are less complex with fewer parameters, making them faster to train while still addressing vanishing gradients. They often perform comparably to LSTMs, but may underperform when very fine-grained memory control is required. What is sequence-to-sequence modeling? Sequence-to-sequence models map an input sequence to an output sequence, often using encoder-decoder architectures. Examples include machine translation, where one sentence in English is encoded and another in French is decoded. RNNs, LSTMs, or GRUs form the basis, sometimes enhanced with attention mechanisms for better alignment between input and output. What is teacher forcing in RNN training? Teacher forcing is a technique where, during training, the true output from the previous step is fed into the RNN instead of the model's prediction. This accelerates convergence but creates exposure bias. During inference, the model sees its own predictions, which may lead to errors compounding. Scheduled sampling is one workaround. What is a bidirectional recurrent neural network? A bidirectional recurrent neural network processes input sequences in both forward and backward directions. This means each output has context from both past and future states. It's especially useful in tasks like speech recognition, where future words provide context. However, it's not suitable for real-time prediction, where future input isn't available. What is an attention mechanism in RNNs? Attention allows RNNs to focus on specific parts of the input sequence when producing each output. Instead of compressing all input into one hidden state, attention assigns weights to relevant tokens dynamically. For example, in translation, attention lets the model align each output word with specific input words, dramatically improving accuracy. What is encoder-decoder architecture? The encoder-decoder framework uses one network to compress input sequences into a context vector and another to generate the output sequence. While effective, bottleneck issues arise when long inputs must be compressed into a single vector. Attention mechanisms were introduced to overcome this limitation, allowing flexible access to the input. What is the role of hidden state in RNNs? The hidden state acts as memory, carrying information from previous time steps into the current step. It's updated recursively, combining the current input with the prior state. This mechanism gives RNNs temporal context but also limits them. Long sequences can overwhelm hidden states, leading to information loss. Compare RNN versus CNN for sequential tasks. RNNs process sequences step by step, making them ideal for temporal dependencies. CNNs, however, can also handle sequences by applying 1D convolutions, capturing local patterns efficiently. CNNs train faster due to parallelization, but they lack inherent memory. For long dependencies, RNNs, or transformers, generally perform better. What is truncated backpropagation through time? Truncated BPTT shortens the backpropagation window in RNNs to a fixed number of time steps. Instead of propagating gradients through the entire sequence, it limits updates to recent steps. This reduces computation and memory use while still capturing relevant dependencies. It's essential for training on long sequences. What is vanishing memory in RNNs? Vanishing memory refers to the inability of vanilla RNNs to retain information from earlier time steps due to vanishing gradients. Essentially, memory of distant events fades away, making RNNs effective only for short-term dependencies. This weakness led to the development of LSTMs in GRUs. How do RNNs handle variable sequence length? RNNs naturally process input step by step, so variable sequence lengths aren't a problem. Shorter sequences are padded for batching, with masking to ignore padded values. Frameworks like TensorFlow and PyTorch provide utilities for efficient handling of variable length sequences during training. What is a hierarchical recurrent neural network? Hierarchical RNNs process sequences at multiple timescales. For example, one layer might capture word-level patterns, while another captures sentence-level dependencies. This structure improves modeling of long documents or structured sequences. By stacking different levels of recurrence, hierarchical RNNs capture richer representations. What is gated recurrent unit GRU? A GRU is a simplified RNN variant that combines the input and forget gates into a single update gate, along with a reset gate to control memory. GRUs are computationally cheaper and require fewer parameters than LSTMs, while solving vanishing gradients. They're widely used when training speed matters. Compare GRU versus LSTM. Both GRUS and LSTMs handle long-term dependencies better than vanilla RNNs. LSTMs use separate input, forget, and output gates with a cell state, while GRUs merge input and forget gates, making them simpler. GRUs train faster and perform well on smaller datasets, while LSTMs may excel on tasks requiring fine-grained control. Choice depends on task complexity and resource constraints. What are memory networks? Memory networks extend RNNs with an external memory component, enabling explicit storage and retrieval of information. They can answer questions by referencing memory slots rather than compressing everything into hidden states. Memory networks influence architectures like transformers that rely on attention instead of recurrence. What is RNN regularization? RNN regularization techniques include dropout, applied carefully to recurrent connections, weight decay, and early stopping. Gradient clipping also stabilizes training. Since RNNs are prone to overfitting, especially on small datasets, regularization is crucial. Specialized methods like variational dropout improve robustness further. What are attention-based sequence models? Attention-based models combine RNNs with attention layers, allowing them to focus on relevant parts of the input when generating outputs. This eliminates the bottleneck of compressing the sequence into a single context vector. These models marked a key step toward fully attention-based architectures like transformers. How does attention improve RNN performance? Attention improves RNNs by letting the model dynamically assign weights to different input steps for each output. This prevents information loss from long sequences and improves alignment. For example, in translation, attention ensures each target word aligns with the correct source words, enhancing accuracy significantly. What is coverage problem in attention models? The coverage problem occurs when attention repeatedly focuses on the same input tokens, ignoring others. This leads to incomplete outputs, like missing words in translation. Solutions include coverage vectors that track past attention or constraints to encourage broader focus. What is Bahtanau versus long attention? Bahtanau, additive, attention uses a feed-forward network to compute alignment scores between encoder and decoder states. Luong, multiplicative, attention instead uses dot products for efficiency. Bahtanau attention is more flexible but slower, while Luong attention is faster and simpler. Both paved the way for self-attention in transformers. What is self-attention? Self-attention computes relationships within a sequence by comparing each element with all others. Each token generates query, key, and value vectors, and attention weights determine how much context to borrow from others. Unlike RNNs, self-attention captures long-range dependencies in parallel. It's the core mechanism behind transformers, replacing recurrence entirely. Why are RNNs less popular now compared to transformers? Transformers outperform RNNs by modeling long-range dependencies without recurrence, enabling full parallelization. They scale better with data and hardware, while RNNs are sequential and harder to optimize. As a result, transformers dominate NLP and even vision. However, RNNs still appear in niche time series and resource-limited tasks where simplicity matters. What is an autoencoder? An autoencoder is an unsupervised neural network that learns to compress input into a lower dimensional representation, encoder, and then reconstruct it back, decoder. The bottleneck forces the network to capture essential features. Autoencoders are used for dimensionality reduction, denoising, anomaly detection, and as building blocks for generative models. What are applications of autoencoders? Autoencoders are applied in denoising images, anomaly detection, dimensionality reduction, and recommendation systems. In anomaly detection, poor reconstruction indicates unusual data. They're also used in pre-training deep networks and generating embeddings. While not as powerful as modern generative models, autoencoders remain versatile tools for representation learning. What is a denoising autoencoder? A denoising autoencoder reconstructs clean input from noisy versions. Noise is intentionally added to inputs during training, forcing the network to learn robust representations that ignore irrelevant variations. This improves generalization and is particularly effective in image or speech denoising. What is a sparse autoencoder? Sparse autoencoders impose a sparsity constraint on hidden neurons, encouraging only a few to activate at once. This forces the network to learn more discriminative features instead of trivial identity mappings. Sparse autoencoders are useful for learning compact, interpretable representations. What is a variational autoencoder VAE? A VAE is a probabilistic generative model that learns not just to reconstruct input, but also to sample from a latent distribution. Instead of encoding to fixed values, it encodes to mean and variance from which latent vectors are sampled. This makes VAEs capable of generating new realistic samples. They're widely used in image and text generation. What is latent space in VAEs? Latent space is the compressed representation learned by the encoder in a VAE. Each point in latent space corresponds to a possible input. By sampling and interpolating within this space, VAEs generates smooth variations of data, like new images or sentences. Latent spaces often capture semantic features. Compare autoencoders versus PCA. Both reduce dimensionality, but PCA is linear, while autoencoders capture nonlinear structures. PCA finds orthogonal components, while autoencoders learn flexible feature representations through neural nets. PCA is faster and more interpretable, while autoencoders are more powerful for complex data like images or audio. What are adversarial autoencoders? Adversarial autoencoders combine VAEs with adversarial training. A discriminator enforces that the latent space matches a desired distribution. This improves generative quality and control, enabling structured latent spaces. They bridge autoencoders and GANs, enhancing sample realism. What is a generative adversarial network, GAN? A GAN consists of two networks, a generator that creates synthetic data and a discriminator that distinguishes real from fake. The two train in competition, improving until the generator produces realistic samples. GANs revolutionize generative modeling, enabling photorealistic images, style transfer, and data augmentation. How does a GAN work? The generator maps random noise into synthetic samples, while the discriminator outputs whether input is real or fake. During training, the generator learns to fool the discriminator, and the discriminator learns to detect fakes. This adversarial game continues until equilibrium, where generated data becomes indistinguishable from real. What is mode collapse in GANs? Mode collapse happens when the generator produces limited variations, ignoring parts of the data distribution. For example, in generating faces, it may produce only one type repeatedly. It occurs when the generator over-optimizes against the discriminator. Solutions include mini-batch discrimination, unrolled GANs, and Wasserstein loss. What are conditional GANs? Conditional GANs extend GANs by adding labels or conditions to both generator and discriminator. This enables control generation, for example, generating digits conditioned on a specific number. They're widely used in tasks like image-to-image translation and text-to-image synthesis. What is cycle GAN? Cycle GAN enables unpaired image-to-image translation. For example, it can convert horses to zebras without paired training data. It uses two GANs with a cycle consistency loss, ensuring translations back and forth recover the original image. This approach unlocked unsupervised style transfer across domains. What is style GAN? Style GAN, developed by NVIDIA, is a state-of-the-art GAN architecture for generating highly realistic images. It introduces a style-based generator that controls features at different levels, enabling fine-grained control over generated outputs. Style GAN powers applications from photorealistic portraits to synthetic datasets, setting a benchmark in image synthesis. What is Wasserstein GAN? Wasserstein GAN, WGAN, replaces the original GAN loss with Earth mover's distance, providing smoother gradients and more stable training. It mitigates mode collapse and vanishing gradients. WGAN with gradient penalty further stabilizes optimization. It became a gold standard for robust GAN training. What is gradient penalty in GANs? Gradient penalty enforces constraints on the discriminator's gradients, ensuring they remain within a stable range. This prevents overfitting and instability common in GAN training. It's particularly effective in WGANGP, leading to higher quality and more diverse generations. What are diffusion models in DL? Diffusion models generate data by gradually denoising random noise. Training involves learning to reverse a diffusion process that adds noise step by step. Recently, diffusion models have surpassed GANs in image quality, powering tools like DALL-E2 and Stable Diffusion. They're slower but more stable and diverse. Compare GANs versus VAEs versus diffusion models. GANs produce sharp, realistic images but risk instability and mode collapse. VAEs are stable and interpretable but generate blurrier outputs. Diffusion models achieve state-of-the-art quality and diversity, though they're computationally expensive. Each has strengths: GANs for speed, VAEs for latent representations, diffusion for fidelity. What is contrastive learning? Contrastive learning teaches models by comparing pairs of samples, pulling similar ones closer, and pushing dissimilar ones apart in latent space. It's central to self-supervised learning and underpins methods like SIM, CLR, and MoCo. Contrastive learning improves representations without labels, boosting downstream performance. What is SIM-CLR? SIM-CLR is a self-supervised framework that uses contrastive learning on augmented image pairs. It maximizes agreement between different augmented views of the same image while distinguishing them from others. By learning powerful representations without labels, SIM-CLR achieves results close to supervised models. What is BYOL? Bootstrap your own latent. BYOL avoids negative samples in contrastive learning. Instead, it trains two networks, an online network and a target network, to predict each other's representations from augmented views. Surprisingly, it works without contrastive negatives, achieving strong, self-supervised performance. BYOL highlights how redundancy reduction alone can drive learning. What is MoCo? Momentum contrast. MoCo builds a dynamic dictionary of representations for contrastive learning. It uses a momentum-updated encoder to maintain consistency over time. This allows training with large, diverse, negative samples efficiently. MoCo is widely used in computer vision for scalable self-supervised learning. What are self-supervised pre-training methods? Self-supervised pre-training creates auxiliary tasks from unlabeled data, like predicting missing parts, rotations, or augmented views. These tasks teach models useful representations, later fine-tuned for downstream tasks. Examples include contrastive learning, masked language modeling, and masked image modeling. It reduces reliance on labeled data. What is contrastive loss? Contrastive loss encourages embeddings of similar pairs to be close and dissimilar pairs far apart. It's the core objective in contrastive learning methods like SIM-CLR. Variants like InfoNCE loss normalize similarities across a batch, making large-scale self-supervised training practical. What are modern trends in generative DL? Trends include diffusion models surpassing GANs, multimodal generation, combining text, vision, and audio, and hybrid methods merging contrastive and generative learning. Techniques like latent diffusion, foundation models, and prompt-driven generation are redefining creativity. The future is moving toward unified generative systems that work across modalities. What is hyperparameter tuning? Hyperparameter tuning is the process of selecting the best external settings for a model, such as learning rate, batch size, dropout rate, or number of layers. These aren't learned during training but strongly affect performance. Tuning methods include manual search, grid search, random search, and Bayesian optimization. Well-tuned hyperparameters often mean the difference between mediocre and state-of-the-art models. Compare grid search versus random search versus Bayesian optimization. Grid search exhaustively tries all combinations but is computationally expensive. Random search samples hyperparameters randomly, often finding good results faster. Bayesian optimization models the performance landscape and chooses hyperparameters intelligently, balancing exploration and exploitation. Grid is simple but slow. Random is efficient, and Bayesian is smart but complex. What is AutoML and DL? AutoML automates tasks like data preprocessing, model selection, and hyperparameter tuning. In DL, it includes neural architecture search (NAS), automated augmentation, and efficient deployment strategies. AutoML saves time and makes deep learning accessible to non-experts, though it can be resource-intensive and less interpretable. What are best practices for tuning learning rate? Start with learning rate range tests to find the largest stable value. Use schedules like step decay, cosine annealing, or cyclical learning rates to adjust dynamically. Warm-up phases prevent instability early in training. Learning rate is the most sensitive hyperparameter, so careful tuning often yields the biggest gains. What is over-parameterization in DL? Over-parameterization means the network has more parameters than needed to fit the data. Surprisingly, deep learning benefits from it. Large models can still generalize well if regularized and trained with enough data. However, excessive over-parameterization without proper controls risks overfitting and inefficiency. What is curriculum learning? Curriculum learning trains models by starting with easier examples and gradually introducing harder ones. Inspired by human learning, it helps models converge faster and generalize better. For example, in language tasks, a model might learn short sentences before tackling longer ones. It's particularly useful for complex tasks or unstable training. What is multitask learning? Multitask learning trains a model on several related tasks simultaneously, sharing representations across them. This improves generalization by transferring knowledge between tasks. For example, a vision model may classify objects and estimate bounding boxes together. Multitask learning reduces overfitting and leverages limited data more effectively. What is transfer learning? Transfer learning reuses knowledge from a model trained on one task for another. In DL, pre-trained models on large datasets like ImageNet provide strong feature extractors. For small datasets, fine-tuning these models improves performance and reduces training time. It's a cornerstone of practical deep learning. Compare feature extraction versus fine-tuning. Feature extraction uses pre-trained layers as fixed encoders, training only a new classifier. Fine-tuning updates some or all pre-trained layers on new data. Feature extraction is faster and safer on small datasets, while fine-tuning yields better results with enough data. The choice depends on dataset size and task similarity. What is continual learning? Continual learning trains models to learn new tasks sequentially without forgetting old ones. Standard DL models suffer from catastrophic forgetting, where new tasks overwrite old knowledge. Solutions include rehearsal methods, regularization, and dynamic architectures. It's vital for real-world systems that must adapt continuously. What is catastrophic forgetting? Catastrophic forgetting occurs when a model forgets previously learned tasks after being trained on new ones. It's common in sequential learning because weight updates overwrite old knowledge. Techniques like elastic weight consolidation, EWC, or memory replay help mitigate it. Addressing this challenge is key for lifelong learning systems. What is federated learning in DL? Federated learning trains models across decentralized devices without centralizing data. Each client trains locally and shares updates with a central server, preserving privacy. It's popular in mobile applications, like personalized keyboards. Challenges include handling non-IID data, communication overhead, and ensuring model robustness. What is distributed training? Distributed training splits workloads across multiple GPUs or nodes to accelerate deep learning. Strategies include data parallelism, where each worker trains on different data, and model parallelism, where layers are split across devices. Efficient communication and synchronization are critical for scaling. Compare data parallelism versus model parallelism. Data parallelism copies the model across devices and trains on different data batches, aggregating gradients. Model parallelism splits the model itself across devices, useful when it's too large for one GPU. Data parallelism is easier and more common, while model parallelism is necessary for massive architectures. What is pipeline parallelism? Pipeline parallelism divides a model into stages placed on different devices. Each stage processes many batches in sequence, like an assembly line. This keeps devices busy and reduces idle time. It's used in training large-scale models where both memory and compute must be balanced. What is mixed precision training? Mixed precision training uses both 16-bit and 32-bit floating-point arithmetic. Lower precision speeds up computation and saves memory, while higher precision maintains stability for critical calculations. Modern GPUs and frameworks support this natively. It's now standard for training large models efficiently. What is checkpointing in DL training? Checkpointing saves model weights periodically during training. It prevents progress loss in case of interruptions and allows rolling back to the best performing state. Checkpointing is essential in long training jobs and is often paired with early stopping to restore the best validation performance. What is pruning in DL? Pruning removes unimportant weights or neurons, reducing model size and complexity. It improves efficiency and can enhance generalization. Structured pruning removes whole filters or layers, while unstructured pruning eliminates individual weights. Pruning is key for deploying models on resource-limited devices. What is quantization in DL? Quantization reduces the precision of weights and activations, such as from 32-bit floats to 8-bit integers. This shrinks model size, speeds inference, and lowers memory use. Quantization is widely used in edge AI, but may slightly reduce accuracy if not done carefully. What is model distillation? Model distillation compresses knowledge from a large teacher model into a smaller student model. The student learns from soft probabilities output by the teacher, not just hard labels. Distillation allows deploying lightweight models that maintain high accuracy, ideal for mobile or edge applications. What is edge deployment in DL? Edge deployment runs DL models directly on devices like phones, cameras, or IoT sensors instead of cloud servers. It reduces latency, preserves privacy, and saves bandwidth. Techniques like quantization, pruning, and distillation make large models efficient enough for edge use. What is ONNX and why is it used? ONNX, Open Neural Network Exchange, is an open format that allows models trained in one framework, like PyTorch or TensorFlow, to run in another. It ensures portability and accelerates deployment across platforms. ONNX is especially valuable in production environments with diverse tools. What is TensorFlow Lite? TensorFlow Lite is a lightweight framework for deploying TensorFlow models on mobile and embedded devices. It supports optimizations like quantization and pruning, reducing size and latency. TF Lite makes on-device ML possible, enabling applications like image recognition or NLP on smartphones. What is TorchScript? TorchScript is PyTorch's way of converting models into a static, serializable form for deployment. It allows models to run independently of Python, improving efficiency and portability. TorchScript supports optimizations and makes PyTorch models production-ready. What is Neural Architecture Search (NAS)? NAS automates the design of neural networks using search strategies like reinforcement learning or evolutionary algorithms. Instead of handcrafting architectures, NAS discovers optimal designs for a given task. While powerful, it's computationally expensive. Recent advances like EfficientNet come from NAS, highlighting its role in next-generation architectures. Why is interpretability important in DL? Interpretability ensures we understand why a model makes certain predictions. This is vital for trust, debugging, and compliance, especially in healthcare, finance, or legal applications. Without interpretability, even highly accurate models may be rejected by stakeholders. It bridges the gap between raw performance and real-world usability. What are saliency maps? Saliency maps visualize which input features most influenced a prediction by computing gradients of outputs with respect to inputs. In images, they highlight important pixels. While simple, saliency maps provide quick insights into what a model looks at, though they can be noisy and unstable. What is GradCAM? Gradient-weighted class activation mapping, GradCAM, highlights regions in an image that contribute most to a prediction. It uses gradients flowing into the final convolutional layer to create heat maps. GradCAM offers intuitive visual explanations, widely used in medical imaging and safety-critical tasks to verify model focus. Compare SHAP versus LIME for DL. LIME explains predictions by approximating a complex model locally with a simple one. SHAP, based on Shapley values, assigns consistent feature importance scores. Lime is intuitive and faster, but less stable, while SHAP is more principled but computationally heavier. Both are model-agnostic tools for interpreting deep learning predictions. What is feature attribution in DL? Feature attribution assigns responsibility to input features for a given output. Methods include gradients, integrated gradients, SHAP or LIME. Attribution helps uncover which features drive predictions, supporting fairness checks, debugging, and compliance in regulated industries. What is adversarial ML? Adversarial ML studies how small, carefully crafted input perturbations can fool models into making wrong predictions. It exposes vulnerabilities in deep learning models. Adversarial ML includes both attacks and defenses, making it crucial for deploying models securely in real-world environments. What is an adversarial example? An adversarial example looks normal to humans, but tricks a model into misclassifying. For example, adding subtle noise to a stop sign image can cause a model to misread it. These examples highlight fragility in DL models and raise concerns for safety-critical applications like self-driving cars. How do you defend against adversarial attacks? Defenses include adversarial training, training on perturbed examples, input preprocessing, gradient masking, and robust optimization. Ensemble methods and certified defenses also improve resilience. However, no defense is perfect. Security in DL is an ongoing arms race between attackers and defenders. What is fairness in ML/DL? Fairness means ensuring models don't produce biased or discriminatory outcomes across demographic groups. In DL, biases in data often propagate into predictions. Ensuring fairness requires careful dataset design, fairness-aware algorithms, and post-hoc bias detection. What is bias in DL models? Bias arises when training data underrepresents certain groups or when models capture spurious correlations. For example, face recognition systems may perform worse on certain demographics. Addressing bias is critical to ensure equitable performance and avoid ethical or legal issues. How does data imbalance cause bias? Imbalanced datasets overrepresent certain classes, causing the model to favor them. In medical tasks, rare conditions may be underdiagnosed by biased models. Solutions include resampling, cost-sensitive learning, and data augmentation. Addressing imbalance ensures fairness and robustness. What is differential privacy in DL? Differential privacy ensures individual data points don't significantly influence model outputs, preserving privacy even if models are queried. Techniques include adding noise to gradients or outputs during training. Differential privacy is vital in sensitive domains like healthcare and finance, enabling safe model sharing. What is federated learning for privacy? Federated learning trains models across decentralized devices, keeping raw data local. Only model updates are shared, reducing privacy risks. Combined with differential privacy and encryption, federated learning powers applications like personalized mobile keyboards while preserving user confidentiality. What are ethical risks of DL in healthcare? DL and healthcare risks include bias against underrepresented populations, lack of interpretability, and over-reliance on black box systems. Errors may harm patients, while opaque decisions erode trust. Ethical deployment requires transparency, fairness, and clinician oversight. What are ethical risks of DL and surveillance? Surveillance systems powered by DL raise concerns about mass privacy violations, misuse for authoritarian control, and biases in facial recognition. Misidentifications can have serious consequences. Ethical use requires strict regulation, transparency, and accountability. What is model interpretability trade-off with performance? Often, simple models like linear regression are interpretable but less accurate, while deep nets are powerful but opaque. The trade-off is choosing between transparency and performance. Emerging methods like SHAP, GRAD-CAM, and inherently interpretable architectures aim to bridge this gap. What is robustness in DL? Robustness means the model maintains performance under noise, perturbations, or distribution shifts. Robust DL models don't break under small changes and handle adversarial attacks better. Robustness testing ensures reliability in real-world conditions. How do you test robustness of DL models? Robustness is tested by adding noise, adversarial perturbations, or evaluating on out-of-distribution data. Stress testing with corrupted inputs reveals weaknesses. Metrics like adversarial accuracy and calibration curves assess robustness. Testing ensures models aren't brittle. What is responsible AI in the context of DL? Responsible AI means deploying deep learning with accountability, fairness, transparency, and ethical safeguards. It ensures models align with societal values and legal requirements. This includes bias audits, interpretability tools, and user protections. Responsible AI is as much about governance as technology. What is green AI and efficiency in DL training? Green AI emphasizes reducing the environmental footprint of deep learning. Training large models consumes massive energy. Techniques like model compression, efficient architectures, and energy-aware scheduling reduce carbon costs. Green AI balances performance with sustainability. What are trends in transformer architectures? Trends include scaling transformers to billions of parameters, efficient variants like longformer and performer for long sequences, and vision transformers for images. Modular architectures and sparsity are being explored to cut costs. Transformers are expanding into multimodal domains, powering foundation models. What are multimodal DL models? Multimodal models integrate data from multiple sources, like text, vision, and audio, into a single framework. For example, CLIP links images and text, enabling zero-shot tasks. Multimodal DL enables richer understanding and generation across modalities, critical for AI assistance in creative applications. What is zero-shot and few-shot learning in DL? Zero-shot learning solves tasks without labeled examples by leveraging pre-trained knowledge, often via prompts. Few-shot learning uses only a handful of labeled samples. These methods, enabled by massive pre-training, reduce reliance on large labeled datasets and allow rapid adaptation to new domains. What is transfer of DL models across modalities? Cross-modal transfer uses representations from one modality, like text, to improve another, like vision. Pre-trained embeddings can align multiple data types in a shared space. This underpins models like CLIP and multimodal transformers, enabling flexible transfer learning across domains. What is the future of DL research? The future of DL lies in scaling foundation models, improving efficiency, and integrating multimodal capabilities. Advances in interpretability, robustness, and fairness will drive adoption in sensitive fields. Generative models like diffusion will reshape creativity, while neuromorphic computing and bio-inspired learning may redefine architectures. The next frontier is combining power with responsibility. You've now explored 200 deep learning interview questions and answers, covering everything from the basics of neural networks to advanced architectures and future trends. Interviews aren't just about memorizing facts. They're about explaining your thought process, solving problems, and showing how you apply deep learning in practice. Keep revisiting these questions, practice them aloud, and connect concepts across sections. The more you explain, the sharper your confidence will grow. Remember, deep learning is evolving fast. What you learn today will empower you tomorrow. Stay curious, keep experimenting, and keep building. If this guide helped you, share it with others preparing for AI roles. And if you're using this in video form, don't forget to subscribe for upcoming interview prep on computer vision, NLP, reinforcement learning, recommendation systems, and generative AI. The journey doesn't stop here. This is just the beginning.